Let's start slowly with the introduction. So this one you already know. So for people who've already seen the context of the workshop, you can have a coffee. And otherwise, I'll start this last session of with a workshop on new geological modeling methods. So this workshop is part of a European project, which is called Geological Service for Europe, and it's coordination and action networking program with the goal to develop harmonized data and information between all geological services in Europe. The idea is to build on what is existing, for example, the HDI system, which has been set up in previous projects, and achieve what is called a geological knowledge platform. And the other objective is to strengthen the network of geological survey organizations. Inside of this big project with various thematics, there are people working on geothermal, on things like that. There is a work package which is dedicated to Geological Framework Setup. And inside of this work package, there is the task I'm talking about, and in the context of which we are organizing these workshops. And it is about sharing methods, open tools, and workflows for specifically 3D geological modeling. And the idea is to strengthen a community that exists both inside and around the surveys. For example, in Europe, there have been many meetings on geological modeling. We have a fifth or sixth one in Poland next spring. So a community that already exists. And this afternoon, after a session yesterday about visualization, a session this morning about geological modeling method, let's say classical or state of the art. Yes, this afternoon the idea was to talk a bit about new geological modeling methods. Again, I want to thank all the speakers who accepted to present their work here. Just remind you that the workshop is recorded. So please, if you don't want to be recorded, just tell us, sending us a mail or saying, I don't want to be recorded. Please try to stick to the allocated time slots so that participants can join when they want and attend the talks they are most interested in. Try to ask your question to speakers with the chat or the dedicated tool. There is a tool, question and answers, or which has this logo on top of the screen normally. And well, it's the third station, so we are not so beginners with the tool, but we are still facing some technical problems sometimes. So thank you in advance for your indulgence. In terms of planning, we had this first session around geological mapping with new methods. So the introduction talk, first talk is by Charlie Kirkwood from the University of Exeter. And he proposes a broader reflection about geological mapping in the age of artificial intelligence. Then Alex Vela from Belgium will present an action which is also in the framework of the GSEU project about an open source solution for mineral prospectivity mapping. Unfortunately, the third talk has to be cancelled. So we will have either a large discussion slot, either a large break, but we will reconvene at 3:10 with a talk by Mike Illier about neural network approach to replace old co-kriging algorithm and other algorithms that have been used for decades now to do a geological modeling. And staying in this framework of deep learning frameworks, we will see how we can use them to generate process-based reservoir models with a talk by Fabien Horst from MinParis. And we will end the session with a talk by Rachel Evan from BGS about using artificial intelligence to extract knowledge from text reports and other information with the objective to use it to constrain or validate 3D geological models. Just a few words about this mailing list. I've put the link in the conversations. Uh, we we had some problems in disseminating the information about the workshop. So if you want to be kept informed about the next workshop, just subscribe to the mailing list. The idea is to keep it very controlled. It just will be an announcement newsletter about the project. So no spamming or advertisement for anything else. And thank you for being here. And I think that, Charlie, the floor is yours. Yeah, perfect. We see your screen.
Okay, but I was muted. I'm not muted anymore, hopefully. Can you hear me?
Yeah, perfect.
Okay, perfect. All right, thanks a lot, Simon. It's really nice to be invited to speak at this, and I've been watching the previous talks and finding it really interesting. Okay, so now I've got, what, 15 or 20 minutes to talk about this. I didn't put a more specific title because I think I want to talk more about, I guess, the kind of overview rather than any specific method. And I know that other speakers are talking more about specific methods. But I guess we all know that we're at this kind of time of technological change and that there are potentially new kind of opportunities opening up for how we could be approaching geological modeling and mapping. So I'm going to try and give some of my perspectives on that, but actually my kind of train of thought in this talk is going to be maybe a bit more experimental than it has been in previous talks. I didn't want to just be repeating myself. So I'm maybe making this one slightly more risky and then maybe slightly more fun to watch. I don't know. So I wanted to just start with a quick note that there is this Geological Society of London special publication in the works, basically, that would be on this topic of geological modeling and mapping in the age of AI. And it's not too late if you want to propose a chapter. Although space is going to be limited, but I just wanted to basically make everyone aware here, in case they weren't already, that there is this special publication in the works, and hopefully this will provide a platform basically for people who are working in this area to publish their work, and we want it to be a kind of diverse collection of people and methods and perspectives. So please feel free to get in touch with any of us. So myself, Christina Ash, Mark Lindsay, Florian Wellman, Mike Hillier, who's on here as well, and Guillaume Cormon. So please feel free to express your interest to any of us. Another kind of notice as well, just to say kind of another thank you to everyone that came and got involved in this AI for Geological Modeling and Mapping conference that we held in Exeter in May, which was, well, super exciting. For me, it felt like there was a real buzz there, and I think there were lots of really good conversations had. So that was really nice, and you can watch all of the talks from that actually on YouTube. We've got this YouTube channel for the conference now, which is YouTube/@AIGMM. So you can look at some of the talks there too. Especially if I do really badly in this talk, you can watch my talk from that conference, which I think was all right. Anyway, okay, so on with mine. So a kind of reflection on how geological mapping has been for the last 200 years. Yeah, so I think we can all agree that it's kind of been focused on drawing these boundaries, the contacts or the boundaries between different units of rock. But if we think about it, well, then what do these lines that we draw on the maps to construct the maps, like what do they actually represent? Well, so we can agree, I think, that each line represents a change in the geological conditions or a change in the geological properties. So, for example, when you cross one of these lines, the age will change or the composition will change, or perhaps all of those will change, or perhaps one of them will just change. Or it could be other things as well that are changing. So the lines represent a change. We can agree on that much. But do the changes in geology occur only where we've drawn the lines? Well, I think we can probably all agree that they don't only occur where we've drawn the lines. So there's a lot of like within unit variability, as well as there is between unit variability. And do all the lines represent the same magnitude of change? And I think we can probably all agree that they don't represent the same magnitude of change. So, you know, some of these are more gradational boundaries than others, say, but just having a kind of discrete line sort of implies a kind of uniform magnitude of change. And then again, is that change happening for all of the properties at once? Well, again, maybe not. And if not, which properties are changing and by how much and from what to what? So I don't know. When we really think about those kind of questions, then I think we might end up wondering a bit just how informative these kind of traditional discrete kind of classification first type maps can be. So with that in mind, then should we focus on delineating where the geological properties significantly change, as in drawing those boundaries, or should we actually focus on mapping the values of the geological properties themselves, which would be, I think, a kind of alternative approach, I suppose. But I know that there are methods that somewhat combine these two at the same time as well. So anyway, if we think about this as a kind of a thought experiment, I suppose, if we could map the geological properties themselves in an accurate and geologically convincing way, then the changes in those properties, which you could think of as being the gradient or the first derivative of their values at any location, it would be self-evident. So if we could map, these properties everywhere, then any location that you query, you could just look at the gradient, and that would tell you basically how quickly are the properties changing at that location. So if you do that, then you can produce a kind of magnitude, a map of the magnitude of change, which is what's here on the right. And I kind of hope that you might agree that this looks a bit like the boundaries that we draw on the traditional classified maps. But there is a bit of a difference, because here it's not just a kind of discrete boundary. It's either there or it's not there. But actually, it can be the magnitude can be continuous. So in some places, the change is very abrupt. In other places, the change is gradual. And I think that's, I think that's fine. I think that's just a kind of naturally the case for the geological system. So we could use this knowledge of the positions and magnitudes of changes in geological properties to then inform the subsequent delineation of boundaries for classification purposes. So I guess I'm trying to make this point that once you have mapped the geological properties, it's basically very little effort to then subsequently classify those or draw these kind of traditional boundaries. But I think it makes sense to start with mapping the geological properties because in this process of classification, actually information is fundamentally lost to quantization error, and we basically can't get that back. So if we start out with our traditional classified map and then want to use that to model all of these specific properties that we're interested in, like geothermal potential, critical mineral concentrations, mechanical properties, and so on, then we're going to be limiting the fidelity that we can do that, because we've already compressed essentially the kind of geological information into that discrete classified representation, which is less informative fundamentally. It's kind of a summary. So just another kind of comparison here is that I realized in thinking about this, as I said, this is kind of experimental trains of thought here, that so this kind of magnitude of change map in the top right, it doesn't exactly look like the boundaries we would get on a traditional geological map, because on the traditional map, the boundaries are basically either there or they're not there. There isn't this continuum of magnitude. And the way to kind of replicate that effect here is actually to quantize the predictions of the continuous geological properties first. So in the bottom left, we've taken our original map of geological properties, which I forgot to say, okay, it's a red, green, blue color scheme. It actually doesn't matter what the properties are. Let's just pretend it's anything you're interested in red, green, and blue. If we then quantize that, so we're reducing it to actually only 8 discrete levels, so 8 different units, essentially, or you could think of it that way. Then when we look at the magnitude of change, or this kind of sum of the magnitude of the first derivatives, then we can see that the lines are tending to be more uniform, basically, because we've kind of artificially discretized the changes so that they're actually sort of uniform steps between these different levels. So I think, again, that's something that we are doing in the traditional geological mapping, but we kind of might not be thinking about the fact that it's happening. But just in the act of making our polygons complete, then somewhere around that polygon, chances are the boundary is actually a lot more gradational than at other points, but we can't really represent that. We have to close the polygon, so we do it. But in doing that, we're kind of implicitly creating this kind of discretization and this loss of information, loss of fidelity. So my pessimistic interpretation of this scenario, I guess I'm kind of diplomatically saying pessimistic, but actually, when I think about it, I kind of think that this is kind of a realistic interpretation. So the traditional geological map boundaries, in some way, they're approximating this kind of summed magnitude of first derivatives, but of a quantized, fidelity reduced map of geological property values. So they're not representing these kind of raw continuum of geological property values, but they're representing these kind of discretized levels of quantized geological property values. And they've got the additional limitation of being, there's either a line, either a boundary, or there isn't a boundary. So they're kind of they're binary. They're either there or they're not there, which again is a very kind of crude way of summarizing these kind of magnitudes of change, I suppose. If you think you can help me explain what I'm trying to say, then please get in touch, because maybe we could make the case more cleanly. Anyway, so what if we don't specifically map geological boundaries then, but we map the geological properties instead? So the downside to this, in practical terms, is that it's not really feasible to map geological properties by hand with high fidelity. So any kind of explicit mapping, I guess, goes out the window at that point, basically. But the upsides are that we can make it happen by moving our geological inference onto computers. And that brings potentially loads of benefits like speed, scalability, consistency, transparency, and other things as well, I'm sure that we could list. And there is this, I think, quite important point that predicted values of geological properties are more easily checked against observations of reality than are these quite subjective positions of geological boundaries. So we've already, I think, kind of agreed that actually there are changes happening everywhere in the geological landscape. It's just that our boundaries try and pick up on maybe the most significant ones. But I think there's a lot of subjectivity in where we place these boundaries. So it's really quite difficult to kind of define some kind of objective function or like error or kind of likelihood function that would tell you, well, how close is this map to reality, unless we're mapping specifically the values of geological properties, in which case it's quite easy. We just go out and measure the geological properties and see how close they were to the predicted ones. So it's a much cleaner, I think, way of comparing the maps with reality. And we heard earlier from Tim, I think you were saying like the importance of validating the models against reality. And well, absolutely, I couldn't agree with that more. I think if we're modeling and not checking how closely it matches reality, then, well, are we really modeling reality at all? So the ease of comparison between geological property predictions and observations of reality make it easy to define and evaluate the likelihood, for example, yes, which is the probability of our data given the model, or maybe more intuitively, you could think of this as being the probability that our real world observations would be produced by the geological scenario depicted by a map. And if you can define the likelihood like that, and that's kind of nice and clean, I suppose, then this in turn opens up the door to uncertainty quantification using Bayesian inference, which tells us that the posterior probability of a map given our observations is proportional to its likelihood multiplied by our prior belief in that map. But I'm actually not going to go into this kind of uncertainty quantification stuff in this talk. I've spoken about it before, and you could look that up on YouTube if you wanted to. So a quick demonstration of this kind of higher fidelity, which comes with associated higher explanatory power, properties first mapping, like I've been talking about. So we can develop machine learning systems to predict the geological properties at any location as a function of position in space, and in combination with all of the available auxiliary information, basically. So, for example, what does the landscape look like surrounding that location at which we want to make a prediction? Or maybe we've got various geophysical survey data that can tell us a bit more than just the location in space, but kind of give us some local context. And so we kind of developed this neural network architecture for doing that in this paper that I published with some colleagues from the University of Exeter in 2022. So the paper was Bayesian deep learning for spatial interpolation in the presence of auxiliary information. And it used this kind of two-branch neural network that could take inputs both from the global location and from these auxiliary covariates, and then process these with a kind of computer vision capability to be able to intelligently predict what the values of geological properties would be at any location, conditional on those inputs. And we demonstrated this using the British Geological Survey's geochemical baseline survey of the environment data. So that's known as GBASE, which gives you stream sediments and soil geochemistry data across the UK, which looks like this on the left. So there's all these different point sampled observations across the map, and these could be of any variables really. And then the neural network will ingest those, and by learning through experience, basically optimizing its output to match the training data. And then that enables us to produce this then continuous map of the geological properties at every position in space. So this is, well, just geostatistics, you could say, but it's using a deep model. So I think it's better able to capture geological structure. So if we didn't have such a system, like that neural network, for example, for performing that inference, we might have to resort to predicting geological property values simply by taking the average of the observations in each polygon of the traditional map, which I think would be, I guess, kind of the simplest thing you could do. But in a way, you could say, actually, that is kind of all the information that the traditional classified map is giving you. So we're just using those boundaries and the knowledge that each unit in the map is different. And then we just take the average of the observations within each unit to be the prediction at all locations within that polygon. So if we do that, and we can do cross-validation here to check how well the predicted values, which are uniform within each polygon, in this case, match the real-world observations, which of course are quite variable. And so here we've got a plot that's got our observations on the x-axis and our predictions on the y-axis. And you can see, well, it's more obvious when I change to the next one, but there's these kind of horizontal layers in the scatter plot here, which is basically showing that for a lot of different observations, we're predicting exactly the same value because it's a static, like uniform value per unit. And the R squareds here are, well, ranging about 0.6, say. So it's something like 60% of variance explained. Yeah, so that's maybe our baseline. So then using the deep neural network approach, now we can make like unique location-specific predictions. So we're not predicting uniform values over any areas, but we're really answering the question that someone might have of what are the properties exactly at this location. Well, we can give a specific answer for exactly that location. And you can see that the R squareds here on held out test data have improved. So we've gone up almost 10% of variance explained by doing that. And when you consider that this actually hasn't used any of the knowledge in the traditional geological map, I suppose. This is kind of learning from scratch. And that traditional geological map, which was the BGS 625K dig map, so that's the kind of official UK geological map that's been in the making for, you could argue, pretty much the 200 years. But taking this different approach, we're immediately seeing, higher explanatory power of the geology. And if you consider that we cannot get a better R squared than 1, that would be like perfect explanation. So this change is actually bringing us between a fifth and a fourth and a quarter closer to perfect explanation, which of course we can never really expect to achieve. So maybe the difference between the baseline traditional geological map and the kind of closest we can expect to get to perfection, we might have gone more than a fifth or a quarter towards that. Now, I just wanted to quickly, I'm very nearly at the end already. I know my time's coming up. I just wanted to quickly go back again to talk about this kind of magnitude of change, or like plotting the magnitude of the derivatives. So we can do that for this map, like for the whole country. And you can see, again, it looks a bit like lines. This is something you could probably happily try and draw with a pencil and paper. And we can compare that directly then. These are the boundaries from that traditional geological map, which is the UK's official geological map. So you can see that, well, I hope you can see that in some way, these are kind of getting at maybe a similar idea, but obviously they've been realized through different processes, and we don't expect them to be identical. It's not like this is a validation of either approach, but it's just interesting to look at them and see that in some way, I think that they are representing the same kind of thing, which is this, where do the properties change? So some kind of summary of all this. The history of geological mapping has been focused on drawing boundaries, but perhaps it makes sense to focus more on the stuff in between. The technologies of the AI revolution, so for example, deep learning, are making it increasingly feasible to move geological inference onto computers with many potential benefits. You could argue that this has been possible since the advent of geostatistics, and I would agree with that, but I think that deep models are capable of representing geological structure better than traditional shallow models, for example, ordinary kriging. And producing geologically plausible maps, so that's maps that contain plausible geological structure, producing those statistically seems to me like a very good way forward, because of the ease of, well, refinement and improvement, but also the ease of the validation and the ability to quantify uncertainty. So from the comparison that I showed, it appears that making such a transition might bring, say, in the region of an immediate 10% improvement to our explanatory power. And actually, as well, I think another aspect of that, I don't think I mentioned this, but the map, the ternary map, red, green, and blue, is a map of potassium, iron, and calcium concentrations in stream sediments, actually. But those are major elements. So you would expect them to be well captured by the traditional geological map, because many of our traditional boundaries are kind of based on major compositional changes. So if we see a 10% uplift even in the major elements, then for more kind of niche geological variables, maybe critical minerals, things like that, I think it's likely that the uplift might be quite a lot bigger. So thanks for listening, and I could just leave these here. A couple of provocative questions. Simon said it'd be good to kind of be provocative. So I hope I haven't been too provocative. But yeah, thanks for listening. That was the talk. I could also, are you still there? Hopefully someone's still there. I have this kind of quick viewer where you can compare between this deep learned map and the existing geological map. And again, I hope you'll agree that you can kind of see the same features in both, even though they're getting there by very different ways.
Thank you, Charlie. Very interesting. It was going too fast at the end, the transition from the maps.
Oh, sorry. Well,
it's okay, but very, very interesting. Yeah, great. I don't know if we have questions from the chat, or yes, there is one in question and answers. What data and map source did you use for Ireland?
For Ireland, yeah. So there is the TELUS program. There's been TELUS Northern Ireland. So Northern Ireland is very densely sampled with geochemical observations. But the Republic of Ireland is work in progress, I think, the TELUS program. So actually there aren't any observations in the central part of Ireland, which is why it potentially looks a bit less believable, let's say, because that's interpolating into open space. Similarly, there's no observations in France that were used, so this is an extrapolation here. But I mean, well, I guess Simon, maybe you can tell me if that
No,
looks reasonable.
I'm afraid I cannot tell you here.
No, well, okay, something we can check.
Yeah, we will check. We will check. Just send us the little map and we will check. A brief one. We were chatting with Nicola and we were asking ourselves, how would you deliver to clients your product that you've been generating with the AI algorithm? Because often the problem with AI is explaining why you chose a parameter. So you would just deliver the value of the property and you say, well, that's it, and do.
Yeah, I mean, I think to some extent, yes, there's various ways that you can try and make the output more interpretable, but there's a quote that kind of comes to mind, which is from, you might have seen recently, there was this Google DeepMind project where they're kind of deep learning weather forecasting instead of using the traditional physical models. And in the paper, I think they had some line which was like, well, we asked farmers, do they want to know what the weather's going to be next week, or do they want to know why exactly the weather's going to be the way it is? And the answer was that the farmers really just wanted the best forecast that they could have. So I guess it's two different priorities, but I think in principle, because it's all there in the model, it's just a question of extracting the kind of reasoning that's going on to produce the output. So, but I think you can do that. And another maybe relevant comparison is that I know that in the UK, lots of the map sheets were mapped by geologists absolutely decades ago. So a lot of those geologists aren't even around anymore. You couldn't ask them their reasoning why they drew a boundary in a certain place. At least here, everything is in the system. We just have to query it.
Yeah, you're right. Yeah. Oh, several questions. What we're going to do is that you have several questions in the chat. We are going to keep them for the discussion slot. Maybe we move. If you want to have a look at the questions, you can, obviously. And you can even answer them if you want. We will switch to the talk by Alex Vela about prospectivity mapping, and then we will have a discussion slot.
Cool, thanks.
Thanks, Charlie. Alex,
Hello.
Hello,
Is it
where are
working?
you? Thank you. Yeah, perfect.
Okay, thanks. Just one sec. Okay, all right. So, hello everyone, and thanks for attending this presentation. My name is Alex Vela. I am a geologist and a data scientist at the BRGM. And today I will not present novel or groundbreaking methods, but I will present our work in the EIS project to produce an open source solution for mineral prospectivity mapping to make it more accessible to everyone. So, first, a quick presentation of the EIS project. So the Exploration Information System is a 36-month Horizon Europe project developing innovative exploration concepts and analysis tools to enhance the probability of finding new sources of critical raw materials for the EU economy. This project is operated by a consortium of 17 partners from European Union member states, as well as from South Africa and Brazil. We have a mixed consortium between research and academia partners and private companies, and you can see some of them here. So what is it about? So the aim of EIS is to provide an environment to manage data and perform mineral prospectivity mapping. For those who are not don't really know what is about mineral prospectivity mapping, the aim of this method is to define the area that are the most likely to host specific mineral deposits, and it's usually useful when performing mineral exploration. This MPM relies mainly on mineral system models, which describe how our deposits are formed, which kind of geological and physicochemical processes will lead to their formation. So there are many components, the energy and heat source, fluid and metal source, how these elements will be transported to the elements that they will be trapped, and what kind of outflow we can expect from this mineralization. We have to transcribe those components into mappable features to use them in mineral prospective modeling. That's where mineral system proxies are used. In mineral prospectivity modeling, we will use those mineral system proxies to define how we were going to treat the geospatial data, so geophysical, geochemical, and geological data, to integrate them in predictive models, which can be either data-driven or knowledge-driven. So the basis of EIS is not only to provide a frame to perform MPM, but also to provide a mineral system library, studying different kinds of mineral system models and giving for each of them the proxies that can be used to help processing the data and produce the favorability maps. In the frame of this project, we are studying three main mineral systems. First, the volcanogenic massive sulfide systems for their potential in cobalt, the granite and pegmatite related system for their potential in lithium, tin, tantalum, and tungsten. And we're also studying the iron oxide copper gold systems for their potential in rare earth element and cobalt. We have multiple test case studies across Europe, in France, Spain, Czech Republic, in Germany, Sweden, and Finland, and we have also a few in Brazil and South Africa. For each test site, we are working with geologists and metallurgists to identify the relevant component and the proxies that can be used to perform MPM. So here you have a small sample of the proxies that can be used to perform MPM for the IOCG systems. We have the mineral system component, what kind of ingredient we are looking for, what kind of data we can extract it from, what kind of proxy we are using. So most of the time it will be distance to specific features or anomalies. And each proxy also have different kind of importance depending at which scale you are performing your MPM. So we have to do this work for the three types of mineral systems. For performing MPM, we have to produce tools. In this case, we have two main tools. First, the EIS toolkit, which is a Python library, which contains all the functions and tools that can be used to perform MPM. We have tools to perform exploratory data analysis, predictive modeling, evaluation. And we have the EIS QGIS plugin, which encapsulates all those tools into a more accessible interface. You don't need to know about Python to use it. And it also integrates all the works done about the mineral systems and gives way to process raw data into proxies that can be integrated into the predictive modeling. These tools are both available in GitHub and open source, so users can participate in their developments and improvement, and you can download them freely. The plugin is actually available via QGIS too. You can download it directly from the plugin manager, and it is regularly updated. The 1.0 version was updated in October. You can launch it directly from the QGIS toolbar, and all the tools that are available in the EIS toolkit can be accessed via the processing toolbox in QGIS. So you don't even have to use Python to access them. We have a wide variety of tools in this toolkit. I won't go through each of them, but you have tools for evaluation, exploratory analysis, filtering, transformation, and raster processing, vector processing. You can perform predictive modeling, and you have a few utility tools. The EIS wizard presents itself that way. You have multiple panels, which are organized in an organic way to perform MPM. First, you have the mineral system proxies, which is one of the most important. It allows you to process the raw data into proxies. So you can first select the mineral system and the study scale. Depending on which mineral system and study scale you have selected, you will have a list of relevant proxies to use with a link to the various components, source, pathways, depositional processes. And you can also create and edit your own custom mineral system and import and export them to share them with other people and other users. Each proxy is also mapped to a specific workflow, so you can directly go from the raw data to the proxy. For example, you can compute distance to specific features. If you have points geochemical analysis, you can directly process them into a till and then compute the distance to specific anomalies. We have the EDA, Exploratory Data Analysis panel, which is optional, but it can give you very useful insight about the proxies and the raw data. You can plot various plot, histogram, bar plot, scatter plot for the raw data and proxies. It can process both rasters and vector layers. You can compute basic statistics, and you have a few tools for exploratory analysis, quiz-square test. You have clustering analysis, principal component analysis, and others. Then you have the second most important panel, the modeling one. It gives you access to all of the tools to perform predictive modeling. First, you might want to prepare your data. So you have the unified rasters, which is mandatory. You have to process your data so they all have the same coordinate system, the same cell size, and are perfectly aligned before being able to do any predictive modeling on them. Those tools are more for fuzzy logic and other type of specific predictive models. You have then the training window where you can select what kind of model you want to use. We have 5 models: logistic regression, random forest, gradient boosting, multilayer perceptron, and fuzzy logic. You can give it a name, choose where you are going to save it, choose what kind of proxy you are going to use for the model, what label it will use, and the parameters and validation setting. You can then test it on a subsample and apply it on the whole dataset. At any point, you can go back in any step and change what kind of model you want to use, what kind of proxy, what kind of parameters you want it to apply. You have the evaluation panel to evaluate your model. So you can compute basic statistics from the classes and the probability scores, accuracy, precision, confusion matrix parameters, AUC score, and you can produce the corresponding plots. All the models are stored and are saved. You can access them at any point after training them. You can see what kind of proxies have been used to generate the model, what kind of hyperparameters were used. You can see when did you train it, and how much time it takes to train it. As of now, you can't really export or import models between QGIS projects or between users, but it will be implemented in the future. I will show you a quick case study that we used to test the EIS toolkit and wizard. So in this case, we want to produce favorability maps of the French Vascan Massif. So on the left, you have the French Massif Central, and on the right, you have the Armorican Massif. We want to produce those favorability maps for tin and tungsten perigranitic mineralization. So it's the second kind of model that I've talked about, the granite and pegmatite-related mineralization. We are targeting Grayson and scan. And we have a few data available: geological maps, geophysical surveys, gravimetric, EM, and radiometric data, as well as geochemical analysis, mostly stream sediment. Using the mineral system library, we can identify a few proxies that can be used to generate our map. For the depositional processes, we can compute the distance to geochemical anomalies, tin, tungsten, and arsenic. We can compute also a few proxies for the active pathways, the proximity to major structures, the structural network complexity, and the distance to the boundaries of major intrusions. And for the source, we can compute the proximity to peralaminous granites, the distance to low magnetic and gravimetric anomalies, and the high potassium and uranium anomalies. So here you can see a few of those examples for the Armorican Massif, the structural network complexity, the distance to peralaminous granites, to potassium anomalies, and to gravimetric gradient. For each of these areas, for the Armorican Massif and the French Massif Central, we were able to compute predictive models. So we use these 3 models because they were the only one available when we did this test. We used logistic regression, random forest, and multilayer perceptron. And we are able to quickly evaluate and compare those models. So in this case, you can see the logistic regression in the left, the multilayer perceptron in the top right, and the random forest in the bottom right. Using the AUC, we can see that the better model according to this metrics would be the random forest, and the least performing one would be the multi-layer perceptron. This approach is also applied on the other test sites. So for the IOCG and pegmatite in Finland, the VMS deposit in Spain, and the IOCG in Czech Republic, it's still a work in progress, but final results will be delivered at the end of this project. The main point being that with the tools provided by the EIS project, we are able to perform those tasks much quicker than using our own tools or made up Python codes. To wrap this presentation, so this project will end in April 2025. The toolkit and the plugin are still in development. We are planning to implement new tools, functionalities, and models. It's still being tested, so we are expected to fix some bugs and improve the performance of some of the tools. If you want to see the documentation, including the manual use for the users, you can access them here. They're still under review from the EU consortium. And remember that this tool is free and open source, so you are free to try it, to comment and suggest anything. And if you like it, I recommend you to start it in GitHub. Thank you for your attention.
Thank you very much, Alex. I was thinking it's a pity that you didn't choose as an example the region that Charlie shown us in northern France, but I think that there are much less granite there than in Brittany. We have 10 to 20 minutes to discussion slot. There are several questions concerning the first talk by about the first talk by Charlie. I'm trying to read them in order. Maybe the first one was about well, there are specific questions. I will focus on a more general one. First one was stating that maybe the focus on the boundaries was the way to focus on the structural framework, because it's the boundaries are what record the fold or the faults. And the question was, could you comment how you would be focusing on stuff between, and if you using machine learning, you could provide such knowledge?
Yeah, I can try and do that. I mean, it's a good point in general, yeah. But I suppose, you could think of, well, so for example, a fault is really like the expression of a very rapid change in properties from one side of it to the other. I guess that's how we recognize it. So if, in theory, your kind of model for predicting the properties is high resolution enough, then the fault should just be apparent within it. You could say the same for folds as well. I mean, you would require, depending on the scale of the fold, potentially lower resolutions might resolve the folds. But then there's also, I suppose, the kind of field observations that you would take, structural observations like dips and strikes of beddings and various foliations and so on. You could predict all of those as kind of continuous fields as well. And yeah, so then in theory, you could have this kind of machine learning system, I suppose, be predicting all of those different properties at once, and also somehow learning how they relate to one another as well in this kind of hierarchical structure that deep models have. I don't know if that's a great answer. I mean, I think basically you're making a good point, and I'm not sure exactly the best kind of comeback to that, but
I think the question by Stefan is related in a way. It's not really on the structural aspect, but on the scale. Is that at some point you want to average some details, and sometimes you don't want to because they have geological significance. And do you think AI algorithm can effectively do this kind of selective averaging? Depending what they learn, I guess.
Yeah, so I don't know. I guess again, I don't know, if you kind of take the thought experiment of having this perfect model that can give you a prediction accurately like everywhere, then you could predict on even the finest scales with that, and that would resolve in theory everything. But in reality, of course, we've got limited number of observations. We don't have like perfect covariates. So I think, yeah, in reality, the kind of resolution that we're going to get is quite dependent on the covariates, or at least if something isn't resolved in the covariates, I think we have to have enough actual observations of it to resolve it through the kind of interpolation alone, rather than based on how it relates to the covariates. Yeah, but the averaging thing, I suppose it's a kind of a fundamental that if you don't know like what the actual answer is, then the safest thing to do is take the average of what the answers might be. So, for example, if you're minimizing like the mean squared error, then you're kind of fundamentally, or it's sensible to be predicting an average of what the outcomes might be. But then in, I guess, more like in Bayesian methods, then you might have your different simulations can actually provide a high resolution realization of what the reality might be. But when you average them, then you lose the resolution kind of fundamentally. So again, I don't know, that's maybe not the best answer, but yeah, it's a good point. Yeah.
Okay.
Good point.
Yeah. Anyway, they're relatively new approaches, so we may have to learn. I had a quick one to Alex. I guess there are a lot of dependencies. I may have missed the point because at some point I had to switch to more administrative task for the meeting, but I may have missed the point. I guess you have many dependencies to implement the algorithm, haven't you?
No, currently you just have to install the QGIS plugin.
But everything comes with the plugin?
Yes.
No external dependencies. So you have coded all the algorithm inside the plugin.
Yes, it's. I think it's an external library that is downloaded with the plugin. In the first iteration of the tool, we had to create a virtual environment for the toolkit, store it in your hard drive, and link it to the plugin. But right now, you just have to install the plugin from the plugin manager, and it will directly install the ES toolkit with the plugin.
Okay.
So you don't really have a lot of manipulation to do.
Okay, but that's nice because our experience with dependencies is a bit hard, I would say, in QGIS. And well, that's the point we could discuss later. And the other one was about the size of the data set that you've already processed. How does it scale?
It's not that heavy, a few hundred megabytes. And the scale is more about a regional scale. But other partners are working at a much larger scale. And sometimes they struggle when using some of the tools in QGIS and the ES toolkit more specifically, because they have gigabytes and gigabytes of soil chemical data. And it can take up to hours to process with the toolkit and only a few minutes with ArcMap. So we still have some improvement to do for some of the functionalities.
Okay. And talking about size, there were also this question from Pedro to Charlie. Could you briefly talk about how your training dataset was leveled? If I remember correctly, your 2022 comprises around 100,000 data points, presumably from different media and taken by different methods. So how that can impact the AI results?
Yeah, okay, another good question. Yeah, you're right. It was over 100,000 data points, yeah, across England, Wales, Scotland, Northern Ireland, and the Republic of Ireland as well. But I think basically data leveling issues are drastically less when you look at the major elements, because I guess they're being counted at like way above limits of detection. So the different labs or the same lab working at different times seems to give a very consistent measurement of major elements. So basically, I think if you look at the major elements, then these data leveling issues don't really tend to be apparent. But I think you're right that if you look at the lesser elements, then it becomes more of an issue, but it's basically not one that we had to solve in that paper. But yeah, of course you would have to solve it. And so you'd have to do some kind of data leveling, yeah, and of course that would affect the output. But I think, well, yeah, it's going to have to be done, I suppose. Otherwise, your predictions are going to be different in different areas when they ought to be spatially consistent. So, yeah, sorry, that's a non-answer because we didn't have to do it.
Okay, no, that's fine. And I had, I don't know, are there any other questions? No, I haven't. I had one to Alex. I was wondering, it's the kind of question that we had this morning concerning the library with several algorithms. You always end up with the question, well, I'm in an operational case. What is the algorithm that I have to choose? So I was wondering, do you try everything? The idea is to try everything and then look at the metrics and choose, depending on what you are looking for, choose your metrics and select the best result, or are there other options?
And in our case, it's more about testing the algorithm and see if everything works fine with the wizard on the toolkit. So I'm testing basically everything to see if at any point it's going to break or not. But it's also about comparing the efficiency of each algorithm. But
Okay.
as of now, I don't think there's any, what do I say, interest in choosing only one. It's more interesting to try a few one, maybe the ones that you are most used to, that you are more able to evaluate, because it's mostly depending, I think, on what kind of data you want to use with your model, because you're not always using fuzzy logic the same way you would use random forest or MLP.
Okay. So it's kind of benchmarking all the available methods. Well, I don't know if there are no more questions. Yes, you have one, Charlie. You have the right to ask questions.
Sort of. It's not much. It's not really a question, but I was thinking about. So Tim spoke in the last session, and he was talking about. I think it was kind of a question then, but I didn't chip in because I didn't have my microphone on. Yeah. So we were talking about how different algorithms or different models produce basically very different outputs given the same data, and yeah, I was thinking about that, and I think it's kind of because the different models have been developed by different people, and the models kind of contain the different prior beliefs of the different developers. So like the natural neighbor and so on versus I can't remember what else, but anyway, they all kind of instill or like embed a different prior belief, I think. So when you it's not surprising that they give different outputs, but also if you were to average them together, you're kind of averaging these different prior beliefs of the various developers that have produced them. But then I think what makes sense for, I guess, us in the geology realm is that really we should be putting the geological prior beliefs into the algorithm or into the model. So I think to do that, it's probably not a case of taking, say, some kind of off-the-shelf algorithm that already exists, but it's more like I think we should be geologists working with model developers to just really put this geological knowledge and the kind of appropriate prior belief in the model. Yeah, I wanted to say something like that.
Yeah, that's right. And that also means translating some geological concepts to the models and implementing rules that, yeah, definitely.
Yeah, which actually might be a good lead into the next talk we have.
And Alex, will the toolkit plugin be maintained or further developed after the end of the EIS project? What are the plans?
So yes, it's a big question because we have found to develop these tools in the frame of the ES project. But for now, the plan is to try to integrate it in a new project for other Europe projects. So try to integrate its development in other projects. And we also, one of the points of making it open source is to see if people will take a hold of it and try to also maintain it, new functionalities by themselves. So it's actually emerged by the GSPO. Yes, it's GSPO. So it's emerged in the GitHub flow of GISPO. So everybody can access it. I don't know if they will keep it forever or if it will go in another repository. But it's still a question as of now as what we will do with these tools after the year's project. And we really want to see them in the future in other projects and keep developing them.
Sorry. Yeah, thank you. I guess unless we have other question, it's time for a break. So thank you very much, Charlie and Alex.
Perfect. All right. So yeah, today I'm going to be talking about GeoINR, which is our neural network approach for 3D geological modeling. Here's a brief outline of the different things that I'm going to be discussing in today's presentations. And I'm going to start with giving the motivations. So the motivations as to why we started developing AI-based methods for 3D geological modeling is simply because of the limitations of existing implicit-based modeling approaches. And some of those limitations can include that they can produce these modeling artifacts in structurally complex settings. And if you look on the lower left-hand part of the slide here, I'm giving some examples of what these modeling artifacts could look like. And sometimes we refer to them as bubble artifacts. And the key point that I want to convey about these artifacts is that the models that are generated are mathematically valid. They're doing exactly what was instructed for them to do and to fit geological constraints. But as we move away from the data constraints, the generated model can produce features that are just not geologically realistic or possible. Another limitation is that they lack the flexibility with incorporating complex and diverse sets of constraints. And I'm giving a number of different examples of that in the lower right-hand corner of the slide of constraints that traditional methods have great difficulty with directly incorporating into the modeling process. And what we want to have in a modeling method, of course, is to have a method that is able to process all the relevant data and knowledge constraints so that we can make the most representative 3D geological model that's most predictive, that also lowers the uncertainty. And the third limitation is that they lack the scalability as we increase the number of data and knowledge constraints into the modeling process, which can limit some applications. So in terms of applications, we kept in mind our objective to support national scale 3D geological modeling initiatives, which are becoming much more common among geological survey organizations around the world today, when we were developing these AI-based methods over the last number of years. One of my colleagues at the survey, Eric DeKemp, he developed this priority map of our modeling efforts across the country. And you can see that in the top right-hand corner of the screen. And as you can see on this map, you can see the top priority is colored in green, and a large portion of Canada for the top priority zone is in the western part of Canada, and this corresponds to the Western Canadian Sedimentary Basin. And so what we aim to do is to apply these AI methods to model the entire Western Canadian Sedimentary Basin, or the WCSB for short. And this is really to support downstream critical mineral prospectivity, which is a part of a new program at the Geological Survey of Canada called Critical Minerals, Geoscience, and Data, or CMGD. Another application that we aim to support is modeling much more complicated structural settings as well in the future. Here on this slide, I want to provide an overview and general landscape in the AI-driven methods for 3D geological modeling. And I want to say that these methods are certainly very promising, but I will note that they remain in a foundational and exploratory stage of development currently, and there's still much to be done. And the revolutionary advancements in deep learning that the world has seen in the last number of years have really yet to be fully leveraged in these 3D methods. But that presents us with lots of opportunities for enabling new and efficient modeling capabilities, taking advantage of things like transformers, embracing the idea of multimodalities, and the emerging idea of agentic workflows. On the bottom of this slide, you can see a number of different neural architectures that have been used for the purposes of generating 3D geological models. And today I'm going to be talking about an advanced approach using the multi-layered perceptron, or MLP. Before I go into the details of our methodology, I want to briefly go over the basis for implicit geological modeling, which is the most advanced type of approach for creating 3D models. And in this type of approach, what we seek to find is a mathematical representation of geological features in 3 dimensions. And we do that using an implicit scalar field, phi of x, where x is the position of a point, xyz, in 3D space. And that gets mapped into a scalar value at that point. And the scalar field interpolates the underlying geometric structure in the subsurface. And this implicit scalar field is approximated and interpolated from given geological observations. And once we have fitted this scalar field function using the data, then we can evaluate that throughout a volume of interest, as I'm showing here. And as you can see, this scalar field interpolates the underlying geometric variation that is sampled by these scattered geological observations. Now, once we have the scalar field, we can then extract geological horizons or surfaces out of that using a very popular computer graphics technique called isosurface extraction using that scalar field. In implicit modeling, we can model lots of different geological features, including unconformities, conformable stratigraphy, intrusions, faults, and shear zones. And typically, there is a separate scalar field that is associated to these distinct geological features, and they get combined using Boolean logic, which associates these scalar fields to particular geological domains. So the fundamental idea that underpins our AI methodology is called implicit neural representations. And so these are neural networks that parameterize these implicit scalar functions phi of x. And what they do is they learn how to map those coordinates into various kinds of representations. And they're very versatile at encoding various kinds of signals, including 3D geometry, images, video, and audio. On this slide, I'm giving a number of different examples and applications and use cases that the AI community and research literature have done. Typically, these neural networks use multi-layered perceptrons as their neural architecture, and these MLPs are composed of 3 different components. We have the input layer, the hidden layers, and the output layer. So in the input layer, that's our spatial coordinates of a point in space, x, y, z. And this gets transformed into a higher dimensional vectorial representation in these hidden layers, generating abstract representations. And during the training process, what happens is it starts to encode much more meaningful information that will lead to better predictions that get outputted in the output layer. And in each of these different layers of this neural architecture, these nonlinear activation functions that are applied to the inputs, and they introduce nonlinearities into the network that allow us to model much more complex signals. So here I'd like to introduce GeoINR. And this is our implicit neural representation networks to do 3D implicit geological modeling. What it consists of is a series of stacked MLPs, which each MLP is responsible for modeling a distinct geological feature. And in this particular example that I'm showing, there are 3 distinct features that are being outputted and modeled. One is the folded strata, the unconformity, and the flat strata. So the neural network outputs these different scalar fields, and they get combined into a resultant scalar field in such a way that respects the geological rules of erosion. And for the training data points that is used for training, we just use the scattered geological observations. And there are some advantages that these types of approaches have over classical or traditional implicit-based methods. Namely that they're very flexible with incorporating data and knowledge constraints, and I'll show how that is done. And they're also incredibly scalable. And one point I would want to mention is that currently we're only training on each data set separately. We're not training on hundreds of thousands of geological models currently, but that is something certainly that we're pursuing. Here, I'd like to give some details about training these neural networks and the mechanism by which we incorporate data and knowledge constraints is through the use of loss functions. And so what these loss functions do is that they measure the error between the predictions that are outputted by the neural network and what they should be for a given geological observation. These errors get minimized during the training procedure, and that is done by updating the network weights through processes like gradient descent and backpropagation in such a way that it will produce a smaller error in following training epochs. And so in every iteration of the training, the model evolves. So that's what the animation that I'm showing here is that the model evolves and it starts to converge. And that convergence means that the errors between what is being predicted by the neural network for the different geological observations is converging or going to 0. And once we have this scalar field, we can extract the modeled horizons out of that using the isosurface extraction algorithms. So key to training our neural networks is the use of stratigraphic relationships. And these stratigraphic relationships, what they do is they characterize the above, below, and on stratigraphic relationships. And we derive them from stratigraphic columns, and we apply them comprehensively to all our data with respect to the geological units and the geological interfaces. And we have developed customized loss functions to measure the errors during training for these types of relationships. So I mentioned that one of the key benefits of these types of approaches is that they're very flexible with incorporating new kinds of constraints and knowledge. And so what we do is we develop a new loss function for that particularly new data constraint or knowledge constraint, and we simply just add it to a total loss or a resultant loss function. And that total loss is what is optimized during the training procedure. So if we had some new kinds of data, we would just add that to our total loss to be minimized. I'd like to show some modeling results that we achieved with GeoINR. And on this particular example, I'm making a comparison between what is produced in GeoINR with a GoCAD SCUA. So SCUA, the results are on the right, the GeoINR on the left. And you can see this is, I should say that this is for the WCSB, the lower Paleozoic portion of it in Saskatchewan, Canada. And you can see by looking at these two different results that they're quite similar. And this is a form of validation, if you will, to support the claim that the GeoINR can generate representative models of basins given this well data set. Moving on to a very different geological setting, this time a deformed metamorphic setting in central Baffin Island, Canada, and this time using an outcrop data set. So we don't have any depth information. We just have whatever has been sampled and observed on the topography and on outcrops. And for this particular case study, the goal was to produce in our models, something that's very close to the generalized source map that you see in the upper left. And so the model results of GeoINR are given on the right. First, on the top side, which we only use very limited interface data and interformational geological unit observations. And what we do is we slice that volume along the topography and compare the corresponding geological predicted map pattern to the generalized source map. And we can see that there's a close correspondence between these models. And we get further a better match with the generalized source map when we add orientation data, which we see on the bottom. So this is adding strike and dip measurements. Here we're moving on to a much larger scale modeling. It's the same WCSB, but this time across Saskatchewan and Manitoba, and this time in modeling all the different geological formations in that basin. So this is a very comprehensive model. It's geographically extensive. It's roughly twice the size of Germany. We use 17 different scalar fields to model that, and using 6.2 million constraints. So that's data plus knowledge constraints. And we do a stratigraphic harmonization procedure, project that into a coherent coordinate system, and the data that you see on the bottom is what is used for the training procedure. Here's the preliminary result that we were able to get with the GeoINR for Saskatchewan and Manitoba. Obviously, there could be some improvements here, but this was done without any fine tuning. And this is the geological volume. And the red line is the cross section, which I'm trying to show here, which I'm trying to highlight the data fitting characteristics of the algorithm on this cross section. One of the other benefits I mentioned for GeoINR is the computational scalability. And this is enabled by cloud computing infrastructure and using distributive training techniques. So for this 6 million constraint data set, we were able to reduce the computational time, which was estimated to take 2,000 years, using RBF-based, implicit-based approaches, just to 35 minutes with our method. And I could say that essentially we can process unlimited amounts of data as long as we have enough GPUs to hold that data and process it. And this is enabled by cloud computing infrastructure like AWS. So next, what we're planning on in the next couple of months is to apply GeoINR to model the entire Western Canadian Sedimentary Basin that spans across 4 Canadian provinces and 1 territory. And this is in collaboration with the Atlas 2027 group, which is updating the 1994 Atlas, which was a very famous publication with industry, academics, and government. And the image that I'm showing here is a clean version of this data set that I cleaned using some statistical-based algorithms. And so now that the data is ready for processing, we're going to apply GeoINR on 6 million top formation markers. And I would assume that this is probably one of the most extensive 3D geological data sets in existence. So really leveraging that scalability. I want to mention some limitations and some challenges with our methodology. It currently doesn't support the incorporation of faults, which is a pretty big limitation. But as of a month ago, there has been a preprint that has been submitted and is currently under review that clearly shows that these type of networks can support the incorporation of faults. So we would have to also incorporate that into our method as well at some stage. I think there's some room for improvement in interpolating finer details, and as well as the regularization method. This is what I'm currently trying to finalize. And going forward, we want to leverage the benefits and the power of deep learning to really integrate very comprehensive geological knowledge and concepts by using a ensemble of geological models into the modeling process at the same time. And there's obviously some challenges related to that. First of all, the lack of comprehensive real-world training data sets. So we would have to augment that with synthetic models, and there's some challenges associated with doing that. So in conclusion, these networks can be used effectively for performing implicit 3D geological modeling. Our neural architecture method, GeoINR, supports conformable stratigraphy and unconformities. It's a flexible framework for incorporating data and knowledge. It's highly scalable. It's effective across different kinds of conditions, settings, and data. There are some limitations which we're working on, and we will apply this method to generate a model of the entire basin in the coming months. And it's a promising area of research that can enable comprehensive integration and improve predictive modeling. And as I said before, the next stage is really to train on large ensembles of models to make the most of the latest AI developments. So thank you, and here are some of the references that I use.
Yeah, a lot of them. Thanks a lot, Mike. Very impressive. 6 million markers. Woo.
Yeah, it's going to be fun to look at the new models for sure.
We can have one quick question in the chat, please, or in the question and answer. And doesn't work. Okay, so yes. I think it's related to the challenges that you've just stated. Are you able to use structural constraints such as fold axis, foliations, etc.?
Yes. Yeah. So any kind of
orientation
constraint that has been used in implicit modeling methods, including fold axis constraints, we've also tested that, and it works well.
Great. I propose, as we are perfectly on time, I propose that we switch to the next speaker. So, Fabien, I don't know.
Yes, hello.
Hello,
hi, everybody.
Here.
Can you hear me?
We can hear you. We cannot see you.
Not yet. See me. The camera.
Okay. That's perfect.
Okay. I share my full screen. Okay.
Okay.
And I try to give you. I hope that you see what I see. So you should have the welcome page for Flumi project.
Yes.
Yes, it's okay.
Yes, the floor is yours. Thank you.
Very good. So let's start. Okay, so my name is Fabien Hors. I work at MIN Paris, and I'm gonna talk about not really a new methodology because FLUMI is not new. But what is new now is that we have built a deep learning approach for generating process-based reservoir mimicking FLUMI. So first of all, reservoir modeling, I think that everybody knows what is it. So we want to create realistic reservoir models in 3D blocks, which match to field data, borehole, seismics, etc. And yes, since 80s and even before, most of models are purely mathematical. For example, geostatistics. Here, for example, you can populate your reservoir with a pre-regression simulation. But we agree that it lacks realism, and there is no really geological consistency between the facies, for example. So we need to simulate physical processes. This was the idea for FLUMI. So let's take an example of a channelized meandering system. For example, a river. The river here, as you can see, a meander can migrate laterally and deposit some sand. Okay. You can have some levee bridges in the system where some sediments are spread far away from the channel. You also have other bank flutes, okay, where you deposit some fine shale really far from the channel. And sometimes you can have some meander cutoff, okay, or with meander that are abandoned with some mud inside the loop. So all these processes have been memorized and mimicked into FLUMI. FLUMI, in fact, is a reservoir model based on the processes, okay, for meandering channelized system. It is coded for fluvial and turbidite systems where you can also see some meanders. It mixed process-based and stochastic approach so that you can have some realization, a lot of different realizations, and then assess uncertainties of the facies model you produce. One constraint for FLUMI is that it has to be executed in the paleogeographical space. Yes, because it's a genetic reservoir model, the space in which we generate sedimentation is the sugar box of the past process. So we cannot handle faults or falls, and it is important to know that. It can generate realistic and various unbodies shapes, like you can see at the right. It is fast and easy to use with only 3 key parameters. And also we can condition it to field data, seismic and wells. Here, the creator of FLUMI, in fact, the name is in the bottom right of the slide, is Simon. Simon from Belgium. It's the first guy that has developed his PhD on FLUMI is Simon. And we keep the technology at the Geoscience Center in Fontainebleau and developed since the 2000 year. I do a quick demo, for example. Here it's FLUMI. You have a 3D view, okay, with a channel and some different way to colorize the properties we generate with FLUMI. Here the facies, for example. Here the grain size. And if you cut the block in vertical section, you can see the particularity of FLUMI, where you can see the adjustment and the heterogeneity of FLUMI by mixing sand and shale. Okay, and if I come back to the 3D view, I just going to okay, so sorry, there is a lag, of course. Okay, so here you can see that the continuity of sand bodies is very important, and you can have a lot of different adjustment, and the heterogeneity is very important for FLUMI. Let's just have a look to a quick launch. So here you can see that the meanders develops and all the processes here are simulated. Okay, so this is a FLUMI, process-based. I said that it was fast. Let's have a look. You can produce a 3D block of 2,000 meters by 2,500 meters and 20 meters thick, so an equivalent of 50,000 years history in 5 minutes using a computer. So this is fast, but not so fast. Is it conditioned? Yes, in fact, we can condition to wells or seismic by taking into account our data and put sand at the correct place while FLUMI is executing. But honestly, yes, we can only handle few constraints. We cannot honor 100% of the facies in our wells, and the techniques we use introduce some artifacts in the model because we do not want to adapt too much the processes in order to honor the facies in the wells. So for these two reasons, for example, here, yes, there is two pictures that explain how it's hard to condition FLUMI while it is running. We adapt with a virtual modified topography processes so that we position the channel at the correct place and we repulse the channel from the wells that are waiting currently some shale. So that's not so easy to condition for me, honestly. The three key parameters are the channel depth, the geometry of the channel, the required net to gross in the final simulation, and the lateral extension of the sand bodies. And with these three parameters, you can obtain a large variety of different simulation, or you can see some scorch views for sand bodies extracted from simulation where you vary the different parameters. So FLUMI, you have some parameters, you give some data, and you obtain conditional 3D simulation. But for each simulation, it takes a while. The idea is to replace FLUMI by neural network. So then you have some parameters, you keep the data for conditioning, but you obtain conditional simulation in only 1 millisecond. How we can do that? We use the generative adversarial network approach, GANs. We train a GAN. A GAN is mean that you train a discriminator and a generator all together. And iteratively, the generator tries to generate FLUMI simulations, and the discriminator will say, okay, this is a real FLUMI simulation, so from the dataset, training dataset, or it's a fake. And while you are trying to minimizing the loss function here. For example, if your trained dataset are celebrity faces, okay, your generator, after training, will know how to generate celebrities that don't exist, for example. So almost instantly. So here, for example, you obtain directly, once the generator is trained, some faces that don't exist. You have a good example online with a website with this person does not exist. Still, in real time, you can generate faces of people that don't exist. Only a GAN has been trained for that. Secondly, you would like that your GAN is conditioned to certain constraints, non-constraints. So for that, for example, we want that the constraint is we want only generate Latina face celebrities, adding funny glasses. Those constraints, how we can honor those constraints? In fact, we add a neural network, an inference model that will produce the random noise that is the sole ingredient of the generator. Those random noise who are particular random noise, knowing the constraints. And by doing this and doing another training for the inference model, we can generate Latina face with the constraints of having glasses. Okay, so this is a small toy example. Of course, now regarding our dataset for FLUMI, here we have 2D dataset of FLUMI simulation, very highly sandy simulations. Okay, 6,000 images in the training dataset. And the architecture we use is the one from Ferdinand Balzar, PhD. It has successfully defended his PhD 2 weeks ago. So here, the architecture of his GAN is a multi-scale Wasserstein GAN with a spectral normalization. It's the result of a long and a lot of different tests between all GAN architecture, possible architecture, and very, very analysis, deep analysis on how to make GANs converge easily. So here you have a multi-scale generator that can explore the latent space in different resolution, so that we cannot avoid some minimal model location. And the discriminator also reconstitutes the whole image through all this resolution. So this multi-scale Wasserstein GAN with spectral normalization can be seen as a proxy of FLUMI. It generates some FLUMI simulation which are close to with the same flavor of FLUMI, okay, and as a two main important feature is that it is stationarity. It is stationary. If you put an input at different size, it can reproduce like a brush the same features as a bigger scale. Also, the second feature is that you can adapt locally. Here, it's not FLUMI, it's plurigression simulation, okay? But imagine that you use the stationarity property to brush, to draw all the contour of this simulation. You can obtain a simulation like that, okay? And you can adapt locally the simulation by not changing the whole rest of the simulation. So here I have the center like that. And if you want to adapt only the center, you can just do a little adaptation locally if the constraints have been different, are different. Okay. Of course, this architecture of GAN works in 3D. Here the dataset are 3D volumes, 3,000 3D volumes. So here what you have to see is that you want to reproduce elongated channels in the 2D slice view, and you want like to come to recover V shapes in cross sections, okay? And the generated ones have the same property. You have elongated channels and V shapes in the sections. What is important to say is that also you can condition it to wells by using our inference model. So here, for example, you have some wells, okay, in your 3D block, and the resulting simulation can be conditioned to wells and honor the facies you have in the wells. Not totally, to be honest. In fact, we cannot get success in having 100% of matching in facies, in well facies. How to be certain that the simulation generated by FLUMI, by our proxy of FLUMI, are keeping the properties of FLUMI and the flavor of FLUMI. In fact, we have calculated some metrics to check if the generated simulation are close to the training dataset in terms of metrics. Regarding the proportion, it's a perfect match. So in fact, the four facies proportions are well respected. And regarding connected components, it is also a good point to see that the distribution of the size of the different connected components are almost similar in the training dataset, let's say the real FLUMI simulations, and the GAN simulation. And it works with more facies. For example, if your dataset is more heterogeneous like that, okay, you can have some generated simulation that looks like FLUMI, but it's not FLUMI. And last thing, but not the least, we have also trained our GAN using a parametric GAN. In fact, all the training dataset is labeled with the two parameters I talked about before: extension of sun bodies and required net to gross. Each picture are labeled, okay, and we give it to our GAN this training data set labelized. And then when we want to generate a simulation, a FLUMI simulation, we can just say, okay, please generate a simulation having those two parameters, with those two parameters, and the GAN can generate FLUMI while interpolating and respecting the two parameters in input. So we are happy with the proxy of FLUMI, and it is very quick. So if I summarize the workflow, you can download and install a FLUMI Python package, which is free by pip install FLUMI and play with FLUMI. So let's have a look to a demonstration of the Python package. You define your simulation grid, you define your 3 key parameters, and then, so here I switch to VS Code, okay, you import FLUMI, you define your grid, etc. You launch FLUMI, it runs during 4 minutes, okay, 4 minutes to build a sediment block up to 12 meters, 9 meters. And then you can show the results in section using matplotlib. So here the facies cross-section, the grain cross-section, and an horizontal slice for the age property generated by FLUMI, also the age. So the iteration where deposits have been generated. So when you are happy with your simulation, your reference simulation, okay, it's time to generate your training data set. So you use cluster because you have to generate a lot of training images. You export them into a file, whatever the format, and then you get the script from Ferdinand Bavzar on GitHub to recover, to download, let's say, the proxy of FLUMI in Python scripts relying on TensorFlow. So let's have a look. Sorry, this is not the correct thing to do here. You go to GitHub. You have the different GANs proposed by Ferdinand. You trained your GAN, and then you generate your simulation instantly. That's all, folks. Thank you.
Thanks a lot, Fabien. Thanks a lot. Very
You're welcome.
impressive. That is so fast.
So fast.
I don't know if we have question. I
don't know.
I haven't seen questions. Maybe in a chat later. Not yet. Have you ever tried? Do you know if some people have already tried to train this kind of models on real data? I was told at some point that Google was providing images of natural features like rivers or deposits, and I don't know if.
As far as I know, I don't know any people that try to use real data for training data sets. Okay. And we use the fabulous FLUMI as our reality.
Okay.
But yes, for sure, we imaginate at the Geoscience Center to build a lot of different other proxy of our models. And maybe it would be interesting to test with real data, maybe satellite images, for example. Yes, of course.
Yeah. Okay. So I think that we're going to switch to the last speaker, so Rachel Evan from PGS. And we are going to try to extract some data from old reports, or maybe new reports also. You will tell us, Rachel.
Yep, I'll tell you.
Yes, we see your screen. Perfect. And
slide, is that in?
We just
presentation mode now?
yes.
Okay.
Perfect. We see.
Okay, great. So a long title, using natural language processing to extract data from reports that could be used for constraining or validating 3D modeling. So just acknowledgement here and expectation management. This is proof of concept work. It's not like fully working system yet. This was done with a few colleagues, but it's building on earlier work that we did a few years ago, and on even earlier work in a more manual pre-NLP AI sense 20 years ago and more. The data is open source, and this was funded by a government grant in the UK. So our motivation, partly that implicit modelling from data points alone can create geologically unreasonable results. So you need to integrate all the data and knowledge inputs into that so that you have your thickness constraints or topological relations. This picture is from a paper that Mike and his colleagues, Marianne Parquet, have produced this year, which illustrates this. And the geoscience ontology, which was created by other colleagues in the Loop project, enables you to explicitly digitally encode this knowledge about these thickness, the topological relations in your stratigraphy. So then you can use that in your 3D modeling or in model consistency checking tools. So this is our motivation. Where do you get this extra knowledge from to help constrain your models? You could get it generated by domain experts manually, but that would be time consuming. But we have a lot of this information already sitting around in these old reports. So can we use AI to automatically extract that and use that and express it in a digital format? So creating new structured data from this old unstructured data. So the AI method is within the field of natural language processing, and that there's is essentially a classification model that can identify entities of interest, so that's named entity recognition, and pairs of entities and how they're related, so entity relationship extraction. So this is our target knowledge. This is just a sketchy class diagram of the sort of information we're after, so rock formations, their locations, lithologies, physical properties, and geometric properties. And this is just an example here from Wikipedia, an actual instance knowledge graph of exactly that sort of information, where each of these nodes and edges are URIs, so they're actually fully specified. So this first step is to identify the entities that you're after. We use some previous work here, so 2018 to 20, we developed this entity recognition model for recognizing formations and geological ages. And this is published on GitHub. The training data is public. This is a demonstration here of our live web service internally. So you can just paste in a paragraph of text here, select the named entities. The pre-trained model that we're using detects the locations and the people and the numbers, but this in addition now collects the lexicon, which is our lithostratigraphic terms, and geological ages. So there is a similar model on Hugging Face as well, a public one, but it says it's been trained on 1 million sentences from this labeled geoscientific corpus dataset, but I can't find that. It's not very transparent. But I gave this one a go using its own sentence that it provides, just a short sentence. So just in a few lines of Python, you can see what this one does. So this again detects locations, geological ages, geological methods, and then a kind of general one, which is just this geopetro. So you can see this is the machine readable data that comes out of it. So it tells you exactly where in the sentence those terms are found. But it's not very good at detecting the UK formation names. It hasn't found those at all. So the next bit here is trying it with our same paragraph. So you can see it detects lots of geoscience type words, but it doesn't really find our formation names. So we're going to reuse our entity model probably, and we realize we have to fine tune one. We're not using one that's already out there. So the next step is the relation extraction. And as a reminder, this is our target knowledge that we're trying to get. This is the same paragraph again. Highlighted here in orange, the formation names. In khaki, these are the lithologies. There's also numerical properties there, like the thickness here, and boreholes. There's lots of other things that we could be detecting. And this is the sort of thing we want to find. We want to turn this into a table of data where we have a subject, a relation, and an object. So the ones useful for 3D modeling would be the overlies, is overlain by type relationships, and any thickness, for example. So there's various methods and algorithms that you could do to address this. Some of them are supervised, some of them just use underlying patterns of grammar and structure of language. There's an unsupervised relation extraction method that is possible. Some of them reuse seed examples from large databases like Wikipedia. So actually our GeoNER model already does this unsupervised relation extraction. So it's open information extraction. Yeah. So you can see the results here. So it's detecting essentially the subject of each sentence and the object, and then the relation between them, which is usually the verb. So this is some use, but it's not as detailed and specific as we would like. So the decision was to address this with supervised learning, so training our own labeled data set, but we'd bootstrap that training data set, reusing all our training data from our previous model, which has got the formations and the ages. We also tried bootstrapping with the results of GeoBert, and also using string matching, using dictionaries for other entities like lithology and events and contact types, and we use the CGI vocabularies for that. Then we use this Decano text annotation software to correct all the auto labels that were wrong or misplaced, and add the relations between them. The training corpus, one sample was taken from the same corpus as our previous work, which is our BGS formal publications called our memoirs, and this is digital text. And then some other samples were taken from archived reports, which are just scanned, one of onshore well reports and one of mineral reconnaissance reports, both from the 70s, 80s. So this is just showing the process. So this is Decano. You set it up with the labels of the entities you want and the relations. So I've loaded these in, but you can create them within the tool as well. Saves them all as JSON in the background. And then for your data set, you graphically annotate. So you pick a span, the start and end of your text. So this one, I'm saying Cadda Formation is a lithostratigraphy. And then this one also is a lithostratigraphy. And then I switch to the relations and pick your subject and pick your object, and then say how they're related. So in this case, this is an overlies relationship. So after doing that for about a week, this is got all these labels for entities, for formations, locations, lithologies, commodities, composition codes, and also I used an ontology for quantity units and dimensions and data types. So whether there were any numerical values, I broke it down in that way. So I thought that'd be useful later on. So you can see we've got quite a lot of lithostrat, over 350 labels for that. There's several others that are kind of in the hundreds, but some we didn't have very many labels on. And then these are the relations. So we've got a lot of relationships between things, and they were observed at a location or observed in a formation. Some overlies, stratigraphic relationships. And then we took that training data, that labeled text, we had to reformat it into a format needed by this, but this is some other open source code from Princeton University. It's a few years old now, but it's fine-tuning an underlying model, Cybert, to do a joint entity and entity relation extraction. It says it's frustratingly easy approach, so I was sold on that. So the results, the model score from the training data we had was only about 0.25. So the F1 score is a harmonic mean of recall and precision. So that's not great. You'd want something more like 0.75, 0.8. So it needs improving with more training data. So we've released the training data we've already done as open source, so it can be built on by us or by others. The auto labeling was mixed success, especially with the dictionaries. Works okay if it's really long and unambiguous words, but otherwise you spend a lot of time deleting labels that were wrongly applied, and it's not very helpful. GeoBert I found not very helpful either. Most of the labels were wrong, and I deleted those from the text. They were too generic, not actually specific classes of information. The biggest lesson was the OCR reports yield very low quality text with lots of spelling mistakes, and there was lots of tables within that data. So we'd need a much larger number of labelled examples to make that work properly. We did actually try to apply spelling correction to the OCR using the dictionaries, but it was overly aggressive and ended up losing information actually. So I removed those training data from the model in the end and it improved the score a bit. But the other point, that there's probably too many labels I was trying to do, and it's an unbalanced data set, so some have only got a very few examples. So if I took out any of the labels with only a few examples, I think that mean in performance would improve quite a lot. So I think we'd be aiming for about 100, 150 label examples for each entity and each relation for a model that then performs well enough to actually be used. So the next steps in this is to augment that training data to improve the model recall and precision. This is all subject to funding, but then deploy it by running it in bulk on all our corpus of knowledge and store it. Also possibly deploy the model in a web service so users can just run it on individual publications. The resulting entities that you've pulled out, if you can link that to a known item in a vocabulary, then we can associate it with its URI, so get the persistent identifiers for those, and making sure we preserve the provenance of each node, edge and graph of where that came from, which document that was found in. And then the output from this we could serialize in geoscience ontology format for use within the other Loop 3D tools. You could serialize the stratigraphic relations in just a standard network graphing data format, and then you can visualize it in a graph drawing diagram. So in theory, you can then visualize the graphs you've got from your literature or from different papers to compare and manually resolve the conflicts. So as an example, this is a handwritten stratigraphic network graph that my colleague Tim Kearsey created of the Midland Valley of Scotland. So just from the knowledge in his head. And this is a stratigraphic network graph that we extracted from our structured database. We just had to extract the entities in this case because the database itself told you which things were in the lower boundary and which things were in the upper boundary. So this is earlier work where we were trying to build a user interface tool to be able to show these different graphs and resolve the differences between them. So you could agree on what your actual stratigraphy was. Just as a note, we're also doing some current work on extracting the data tables from these reports. So they're not suitable for this technique of relation extraction, but they are really useful for other things. And this is for minerals data in particular, the Critical Minerals Intelligence Center that BGS hosts. So that's a image recognition problem. So you detect the tables within the scan of the report, then you detect the structure of the table, and then you OCR within each cell of that. So in theory, this is generating lots more data that you can use in modelling. So in particular, any stratigraphic knowledge of which formations overlie each other or what the maximum thickness are, you could programmatically rule out unreasonable models that have been generated from some implicit modelling, and reveal any inconsistencies between your model, between a 2D map, maybe from map to loop has turned it into a 3D model for you, and from the literature. So my provocative points at the end, have any of these been tried in practice though? Is it useful? And any output from this automated extraction is going to introduce new errors. It's not always going to get it right. It will add incorrect things that you have to go back and validate. Is this saving people any time, or is it sufficient just to provide the data discovery and let the users build that knowledge graph more manually and sort of manually reference where they got that from? So this is what we get to find out. So that's all I have. Thank you.
Thanks a lot, Rachel. It's always a bit frustrating when you are a webinar because you stop talking and there's no noise. That's excellent. I was concerning your last slide. I was just thinking to myself, maybe it's we will always need something that is visual. We have to look at the model. So I don't know if the graph is too complex. How easy it is to check the validity of the graph instead of just looking at the model. And so tools that are extracting automatically and generate a model that is consistent with the graph, I think are very useful just to think as geologist, I guess, looking at what you see. I don't know what you think about it, but
yeah, alongside most of our published maps, we have these generalized vertical sections, which essentially are the stratigraphic column for that area. We don't have that as a database. We have lots of these sources of this knowledge, but we don't have it digitally anywhere. So I suppose the geologists are used to seeing these generalized vertical sections, and presenting it in that sort of way might be easier for them to compare then, rather than the nodes and edges of the simple graph network.
okay. And is there a plan to deploy this at PGS on a medium term? I was just wondering, how far are we from deploying this?
Well, yeah, we need some more training data. Otherwise, it's only coming up with the right answers about a quarter of the time, or it's missing, 3/4 of the things you want it to find. So yeah, that training data, once you get going, it's just a process to go through. And actually, if I focused on fewer labels, then it would take less time. So a bit more funding, maybe in the next year or so, we hope.
Okay, next year.
Yeah, but the data itself is released just about now. What training data we do have.
We have a question where I think we're going to switch to more general question to everyone, but to every speakers. We have a question concerning image recognition. Is there any possibility to extract data from all drawing, and particularly co-drawing, often found in well drilling reports? I had read some very interesting paper stating that geology had developed the day we had been able to reproduce drawings, and I think it's not so false. So can you handle these old drawings?
It's a different technique than the one I've presented here, but yes, like a few years ago we were looking at this problem, trying to get answers from well logs and from drawings of the log, and at that time it would have needed some training data and some labeling, but actually recently the latest foundational models seem to be able to do that already, to be able to interpret the contents of these images quite well. So yeah, it's something we're interested in, definitely.
Okay, that's Tim is stating that the network graphs are useful to understand the issues where there is contradiction in the strat between different maps and models. Yeah, I was wondering also, and maybe it's a question to the three of you. It's the usual question: how far away from extracting knowledge with your techniques, passing it to GeoINR to model the boundaries, and then populating properties with something like what Fabien presented in between the boundaries, and have this kind of automated workflow. It was a bit the question about, as of today, how can we insert this AI stuff in our current modeling workflows, and what is the next future, or according to you?
Yeah, we're in the early stages in BGS of developing AI ethics guidelines. There's some, you have to consider, if you're using a third-party model and you're sending your information up to someone else, then you have to make sure that you're happy to put that in the public domain. But if you self-host one, then you need to have all the infrastructure to do that, to host it all, so it's a closed environment. But we are starting to have those conversations about self-hosting an environment and being able to trawl through all our own BGS reports internally and build this sort of system.
Okay, Tim, you wanted to react?
Yeah, I think so. I have been using some of these systems in some of my day job. Obviously presented some of that with how we're looking to move the superficial thickness model on, which is, I think, the only thing we've really done in the 3D space. But we have used more generally machine learning to improve mapping, to do automatic feature mapping, and then in the network graph things, I was actually using the map to loop outputs. So I don't know if you've used map to loop, but one of the things that comes out of that is a network graph. And that as a piece of, again, I've recently used this in a new remapping project where we've got severe edge match problems on this basin. And it was actually that it was using map to loop and getting a network graph out of that made me go, oh, okay, there's something quite fundamentally wrong with the stratigraphy in this basin. Like 3 units which are stratigraphically should be at the same stratigraphic level. And that was then the point that I then used to then go back to all the chronological data and realize that basically the chronology was done 30 years ago and it's moved on, but our stratigraphy hasn't. So they are useful in that sense of trying to get to problems that you may have with particularly old mapping very, very quickly. So we're starting to use them.
Okay, Mike, you wanted to react?
Yeah, just wanted to make maybe a comment related to like the broader use of these AI tools among a wider range of practitioners. I think like currently today, like the things that I've done so far is very specialized. Like you need to know Python, you need to know scripting, you need to know how to translate some of your geological knowledge into some of these parameters, right? So I think there needs to be a lot to be done to give a tool that a wider audience can use. So I think having some sort of user interface is like probably step one, instead of like a Google, like a Python terminal. But I think a lot of the work that Rachel's doing is incredibly powerful in terms of extracting the knowledge in terms of a graph. And these types of representations can be easily translated into my methodologies in terms of constraints and things really easily. So having those tools available certainly aids in making that process a lot better. And to go back, I guess, on having tools that are better of use to wider audiences is to also sort of give acceptable ranges on some of the knobs on the hyperparameters that will be useful for people in certain geological settings, for example. So yeah, that's just a few comments I had.
Thanks. There was also an interesting question from Jan in the chat, and it's about the language that we use to describe the geology. So do you think that once the tools are trained in English, we just have to translate the language and it works, or do we have to retrain them in our own language? I can read the exact question from Jan because it's a bit a reformulation. I thought it was very interesting. Once the automatized data mining from archival materials will one day work well in English, do you think it would be relatively easy to train it also for different languages?
Well, a lot of foundational models are already trained in multiple languages. So if the foundational model that you're fine-tuning with this is, then yes, it will work. But you'd have to start again with your own training data, labeling your own French terms, I think. That's the limit of my knowledge at the moment. But yeah, you don't have to start from scratch retraining a whole large language model if that's got that language capability already.
Okay, Mike seems to think that ChatGPT is enough. I don't know. I don't know. Our special, maybe you need something special related to geological concepts or knowledge. I don't know if maybe as special as ChatGPT, you mean, Mike, not a generic.
Yeah, I think there's some new foundational models that have been specialized for geoscientific inquiry. So, I mean, but generally my comment was like these language models like provide that translation capability. But yeah, something that's been more trained on specific data is something that would be better.
Definitely. Don't know if there are other questions. No. Charlie.
Hi. Yeah, me again. Well, I was thinking if there isn't another question coming up anyway, then I guess I have a question for you, Mike, which is, yeah, I was wondering about the ISO surfaces that you're talking about in your work, and how similar do those end up being to like the traditional boundaries that we would have in a traditional map? That's the question. Yeah.
Yeah, the boundaries that I'm extracting from a continuous variable are those, they correspond to the boundaries that you would see in normal maps. Yeah.
Yeah, okay. But the ISO part of the ISO surface means the properties are like consistent all along that.
Yeah, they're the same along that surface. So that's just the way that we model it in implicit modeling, like along that interface, it has the same scalar value, and it's just how we set up the constraints to extract that, and it's consistent along those data points sampling that boundary.
Yeah. Yeah, okay. But then when I think about, I don't know, well, I mean, I know the UK geology better than Canadian, but when I think about where some of the boundaries are in our traditional maps, then I don't think that they are in like positions of uniform properties, say. It's more like, I guess, where there's been a big change in time or in some other properties. Yeah, I don't know. I'm just curious. Maybe I'm.
Well, it's fuzzy. The boundary is fuzzy. It's uncertain in most places, right? So you can do ensemble modeling with these kinds of approaches and look at the variance of all the models that are, and then you can kind of see the confidence zone for that boundary within some region.
Yeah, no, sure. I don't know. I wonder if a field geologist thinks that they're mapping an ISO surface as well when they're drawing the boundary. I suspect that maybe not. I don't know. Anyway, that was my provocative question again.
Sometimes the time surface is a time surface. Sometimes. I had one specific question to you, Mike. You said you were training scalar field separately in your model. And but the disjunction between the different scalar field is made inside the model, or do you train them separately and have several train
Oh no,
model for it?
they're coupled, so they interact
Okay.
together.
Okay, so in the training phase, you have all the scalar fields and they interact.
Yes.
That's what.
And that's one of the unique benefits too, right? Because traditionally, each of those scalar fields have been fitted independently, right?
Yeah.
That can give rise to some issues.
Okay, that's nice point. Yeah, no. Mike, a question for you. The GoCat square maps shows many pimples on model surfaces, which were smoothed too much in the mean average approach. Can GeoAina sort this out by fitting surface more closely to noisy data? From Zbigniew.
Yeah, so that's something that I've actually been working on in the last 6 months or so. I made lots of progress with that, and just not really ready to show the results, but the results are encouraging. So the way that we fit it more closely to more like locally variant structures is we use different activation functions that enable that capability. So the latest in implicit neural representation networks, they use periodic functions that enable you to better model fine details.
Okay. Wow. I guess it's, I don't know if someone else has a questions. Otherwise, I may close the workshop. I don't know if someone has a comment. I wanted to give credit to the core team of our task, because we're not only Nicola and I behind this workshop. We've been talking about the content of the workshop with all the people from the core team of this task. So we are a small group of people from the five or six, five green surveys here on the figure. So you've seen some of them, but not all of them were there. So I just wanted to give back credit to them. And I wanted also to thank all of the speakers that have accepted the task to present during this seminar. It was really great, I thought. Yep, just to remind you that we have been setting up this mailing list. If you have any comments about how the workshop was organized, just send them to us. We'll try to make things better the next time. And unless someone has something to say, I might close the workshop and thank again everyone. Yeah, thanks to all speakers for the great talks. And bye-bye.